Ryan Voigt, and climate modeling.
Well, thank you. It's an honor to be here tonight. Thank you for the organizing committee of the Science Cafe series to invite me here. Thank you for all of you coming and spending an evening with me and talking about what I think is one of the most important environmental issues of our time. So I am in the geography department. I'm an associate professor for those of you that do not know me. And my research is focusing on Antarctica and the southern hemisphere climate. I use climate models in my research to answer questions about understanding the human footprint on climate change going on in Antarctica. And I use climate models also to understand interactions between other parts of the planet and Antarctica. But I'm not going to be talking to you tonight about my own research. I'm going to actually kind of continue the theme of this week and talk to you about an important topic that would across many disciplines, and that is of climate modeling. One of the things that I've been doing is leading efforts on the State of the Climate report, and there are several of these on tables throughout the cafe tonight. You're welcome to take these home with you. I have plenty more. They're available online, but I've been an associate editor for the Antarctic chapter on this report. And this report serves from the National Oceanic and Atmospheric Administration, NOAA, to be the assessment of the state of the climate. And it gives you a snapshot of each year's climate. This is the 2013 report. And it tells that what's happened in that climate year in a historical perspective. In other words, how unique was that one year compared to the records that we have of data? You're welcome to take this home and get some information about what happened in 2013. This is a picture, of course, of the Philippines after Super Typhoon Haiyan moved through there, and then a great satellite image of it on the back there. It's loaded with a lot of interesting information. It's not so much a climate change report because we don't actually try to understand what's causing the changes, but more understanding what happened. So it's more of the what that happened as opposed to the why it happened. So please feel free to take that with you. So before I begin, I have two main goals. And if you get these across, then I'll feel like my night was successful. The first goal is that I want to convince you and build a case that weather forecasting is a lot different than climate modeling. And if you don't like weather forecasts and don't trust weather forecasts, that should have no bearing whatsoever on your belief about climate change and what climate models are telling us and for climate change. That's one goal. The second goal is a bigger goal, maybe a little bit more lofty here. I strive to teach you tonight in some way that climate models are really the only tool that we can use to understand the human footprint on climate change, what's going on right now, and they're the only tool that allows us to see into the future and what possible scenarios there might be for our future climate. So they're absolutely crucial for understanding the science of climate change and, in particular, the why of climate change, what's causing the climate to change. But before I begin, I think we'll have to clear the air a little bit. So this week, Sunday was an important climate day. There was the climate march in New York City. Monday was the equinox. That's pretty exciting. Yesterday was the UN panel climate summit where President Obama spoke. And if you heard that speech, I thought it was filled with some optimism, some hope if we do make some policy decisions here on how U.S. might be on board more in the global arena with climate change. I'm not nearly as exciting as any of those things. I'll tell you that right now. Those are really exciting things. But I think there's a lot of momentum going on in understanding climate and appreciating climate. But the air that I need to clear is that you probably have a bias against climate already if you watch weather forecasts. How many of you today looked at a weather forecast? How about in the last week? Why? Give me some reasons why you looked at a weather forecast. Shout them out. What to wear? What else? Whether to bike to work. Travel, right? To plan activities outdoors, whether your picnic or event is going to work. Yes? Water the garden, yeah, if it's going to rain or not, right? You probably have a lot of interest because weather is impacting your daily life. Now, those forecasts that you looked at, how many of you believed them? How many of you trusted them? A lot less of you. Some of you. Yes. I've heard it all. I've been in the field for about 15 years. Weather is one field where you're always wrong and still get paid. You know, we're just throwing darts at a dartboard and whatever it hits is what the forecast is for that day. We're shaking an 8-ball in our office and, ask again later, sort of thing. I've heard it all. And I bet you have been frustrated many times with your weather forecast. So I want to clear the air and tell you at least one reason why weather forecasting is so complicated, and then I'll set the stage for why that climate modeling is totally different of a problem and a different approach than weather forecasting. The idea behind weather forecasting stems from this idea of chaos theory. Has anyone heard of chaos theory? It's a scientific principle dealing with dynamic systems. And by dynamic system, I mean these are systems where individual processes are interacting with one another and they're influencing each other so it's such a way that they're not separated, but they're always in interplay, and that they're going to continue to influence each other and create more chaos, more complications, more interactions in that system with time. So to give you an example of a chaotic system that's universal to all of us in this room, no matter what your area of study is, your focus here in college, we can think of something that's similar to all of us, and that is our own lives. Our own lives are a chaotic system. There have been many things that have influenced your life daily that have led you to be the person that you are today. There have been situations in your past, even within a few hours or weeks from now. There have been people that have influenced you. There have been places that you have been. There have been lectures or thoughts that you have heard that have changed the direction of your life and made you who you are today. We're, as meteorologists, in charge of interpreting chaos like your lives, except in terms of the atmosphere. So let's see how good you are at thinking of prediction in terms of chaos. How many of you could say confidently that you would have predicted that you would have been here tonight yesterday, a day ago? Some of you. How about a week ago? All right. You heard about my talk maybe or something. I'm honored that you knew about me and wanted to come. That's great. Let's make it a little harder, because that's not specific enough. How many of you knew where you might have sat in general tonight? Your location? 2 or 3 of you. Let's go even deeper. We're not dynamic enough yet. We're not complicated enough. How are you feeling? Your mood is very dynamic. It can change by the minute, by the hour. All sort of external forcings and internal forcings are changing your attitude and your perception. How many of you could have predicted your specific feeling, both physically, mentally, everything, how you would be feeling right now, even as quick as like 6 hours ago? Oh, getting harder, right? Getting harder. Yes, this is the atmosphere. One process in the atmosphere influences another down the stream in such a way that after time, the air can get so large that it's really hard to know the final outcome. There's this famous scientist, Edward Lorenz, who developed this idea of chaos theory, and there are 2 curves here. And they are starting out with basically almost the same initial condition. The difference is 0.000127 between these 2 curves in the initial starting point. And you can see as they run forward in time in a dynamic environment that they diverge completely and actually give you a final outcome that's completely different. 2 scenarios started almost exactly the same, completely different outcome in the end. With weather forecasting, we're taking all the data that we can from observations, ground-based, air-based, satellites. We're assimilating those into our models, and that's our initial state. One model is going to be a little bit different from the next in terms of its initial state, and that gives you a different outcome in the end. Especially as you move further and further in time, you can see how chaotic those become and how different they become as they move further down into time towards the right there in those graphs. For an example here, this is a weather forecast image taken Friday during the midday, one of our main US forecast models, and it's sea level pressure concert here, and the shading is precipitation. And if you watch it through here, you'll see that there's a band of precipitation just starting now over the Great Lakes in Canada, and it'll move down over into Ohio on Sunday of the weekend here. And you'll notice that it's pretty widespread, right? There's precipitation going over the whole state, and there's some hot spots where you have a little bit more precipitation accumulating in this forecast. That's one model. Here's another model started at the exact same time with about the same amount of data here. Now this one goes a little bit farther into time, all right? So it has a little bit more, it's coarser because of that, and it has a little bit different looping. It's every 6 hours here. But you'll notice that there's a big difference in this model in the way the precipitation looks as it moves across to Ohio. There's a difference in the timing. the intensity, the duration. And you know what? Neither of these were right? If you're out on Sunday and you're watching the rain, I happen to know this from personal experience, that it did not rain everywhere across the state. And even in Athens, the precipitation was very, very spotty. My family, being the meteorologist that I am, I'm looking outside, look at the radars, clear skies. Radar didn't show anything. I'm like, let's go to the bike path. I looked at the forecast, it wasn't going to be that bad. Walked to the bike path. We're out on the bike path. My two girls, my youngest in the Hot Wheels car, my oldest in her bike with the training wheels that we lugged in my car without a bike rack. All right, to the bike path. We're out there. We're past Peden, and we're going around the curve of the golf cart track, going across the bridge there, across the river, and it cuts loose. It just pours. And my kids are like shivering and bundled up, and we're like at the point of we have to decide if we want to turn. I'm looking around, it's blue skies. This cloud is just sitting right over us, and in fact it did. Right? Athens and the campus area got quite a bit of rain. Our rain gauge out on West State Street by the ball fields only measured 3 tips of the bucket, 3/100ths of an inch. My house in Hickory Hills, south and east of town, bone dry. None of these models were right. You can see there's a lot more precipitation that they were forecasting to come across the region, and it didn't validate. Our job as meteorologists are to interpret this chaos and provide you with a numerical value that you want to know. What's the rain going to be like? How much is it going to be like? When's it going to happen? What's the probability of that happening? It's not easy. So yes, we are wrong sometimes, but I don't think we're wrong as much as the models are wrong. Now, that might scare you. You might say, okay, these models are wrong. How can we then, if we're predicting weather here, how can we ever predict climate? And that's because climate is completely different than weather. Let's talk about climate real quickly. What is climate? Anyone? How would you define it? Yes.
Weather average over a long period.
Brilliant. Yes. I'm going to simplify it here and just repeat what he said. It's the average weather. The word average is important. And the average period for most climatological data is at least 30 years. All right, we're looking for norms that happen of at least 30 years. Why? Because we want to average out cold years and warm years, wet years and dry years, things that are happening interannually, one year to the next, that might have lots of reasons why they're occurring. We want to kind of average those out to get what you might see in the middle here, the average weather. So it has parts of weather in it. Obviously, weather is influencing the average and therefore influencing climate. But what we're looking at is something more statistical here, right? When we take data, add it up over time, and get a mean value. Because it's different than weather, what you're looking for precise variations, day-to-day variations in the conditions outdoors. Climate is not that. I've heard this proverb, and I think it kind of explains it pretty well. Climate is what you expect, the average for the day. Weather is what you get. You don't always get what you expect, right? The average temperature right now in Athens for this time of year is supposed to be on 75. Today we were below that just slightly. This end of this week we'll be above that. Right? We don't always end at 75, even though that's what we expect. So when we predict climate forward into time, we're going to do it in much more of a statistical way, rather than here's what it's going to be like on this day, here's when the rain's going to happen, and this is how long it's going to last, and this is the amount of rain that we're going to have. We don't do that when we predict climate. In fact, this is one more thing I want to show you about this. If you think forecasting weather is bad on 3 days, and this is not my data, and this is not my website, but there are companies out there that will give you monthly forecasts. This is the October forecast for Athens by some company. This is chaos theory stretched to the extreme, where you're now predicting things a month more in advance. Just for fun, because we all can relate to a specific date on here, let's just see what happens in Athens to validate this model forecast. Here's homecoming, October 11th. They're calling for 61 and abundant sunshine. Just remember that number in your head, and let's see if it's actually abundantly sunny on Athens homecoming or not. I don't know. I wouldn't bank on it here too much. Don't plan a big party outdoors that you can't cancel because that's more than 2 weeks out yet, and that's dodgy at best. But in climate, we don't predict numbers like that. We don't predict conditions. We predict whether or not it's going to be above or below normal. We use averages, statistics to predict climate. So this is actually our weather forecast, our climate forecast, if you will, for this winter. And we're using things like sea surface temperatures and other stable parameters in the atmosphere and ocean to predict what it might look like this coming winter. This is from the NOAA Climate Prediction Center, our main US governing body on climate prediction. And you can see for Ohio here, EC, equal chances, meaning we're not really sure. It has about the same amount of chances of being warm as it does as cold. Right now, it's kind of a coin flip as far as how this winter is going to be. But that doesn't mean we have skill in other places. Here, the A and the B, this is above normal temperatures they're predicting for the northern and western parts of the states. And then the southern parts of the states are actually predicted to be a little bit colder than average. This is a typical El Nino type pattern, which may happen this winter, and that's why a lot of these patterns are looking that way. But it's totally different. They're not going to give you any numbers with any of this data. It's all whether it's going to be above or below average. And so because of that difference between weather and climate prediction looks quite a bit different too in terms of climate modeling. All right, let's talk about this. What are some things that you think are important when you think of climate that you would want to include in a model? Okay. Air temp. Precip. What else? What's that? Humidity? Okay. Good. Yes, moving away from the atmosphere. Ocean. Temps. Air pressure. Can go in the atmosphere here. Great, you guys are awesome. Keep going. Horse? What's that? Forest, yeah. We'll call this land cover and land use. Tides, yeah, oceans. So let's do currents and tides. Perfect. Yes. Topography. That goes in, yeah, I'm not going to lump that in everything. It kind of goes with the ocean, the bathymetry of the ocean, but also the land cover. Good. Let's think colder. Yes. Yeah. Storms. I'll just call it like you did, for lack of simplifying it.
How about snow?
Snow, ice. Right? These are all part of the global climate. We're thinking Athens maybe too much right now. So moving to the polar regions. Snow and ice cover, right? The seasonal sea ice cover in the Arctic or the Antarctic, the land ice, glacial ice, whether it be on mountain glaciers or ice sheets like Greenland and Antarctica. We need to all account for these things. They are all things that influence global climate. What I'm going to talk to you now about is this particular type of climate models called coupled climate models. And these models are the state-of-the-art models that we're using now for policy decisions across the world. And they will lump them into 4 categories of models. This model here would account for everything that happens in the atmosphere. You listed quite a few of them. But anything, that, even cloud cover, and whether or not clouds are forming, hurricanes, all these things that happen in the atmosphere are accounted for by one model. We have a model that simulates processes in the ocean, things like ocean currents, tides, El Nino and La Nina events, the Pacific decadal oscillation, the Atlantic multidecadal oscillation, all these climate features that are part of the ocean. Here, another model, land cover, but you can also think of ecosystems, including people, all get lumped into another model for the land. People's influence, whether we're cutting down trees or building cities, all get modeled and simulated because they all affect climate. If you're building a city, you're changing the albedo, the amount of reflected radiation from the sun, and that changes how much heating or cooling is going on. If you're cutting down forests, you're changing not only the properties of that land cover, but you're also changing the flux of carbon dioxide from the plant life that used to be there previously. And then this model here gets lumped into what we call the cryosphere, which covers all basically frozen water, snow, ice, glacial ice, but also grounded ice, sea ice cover in the polar regions that form seasonally. And what happens in these models is that we have these 4 things running separately, but like the real world, they're communicating all the time. So we have a model for the ocean that is going to be influenced by what happens in the atmosphere. Obviously, if you're over the ocean and the wind speeds start picking up in the atmosphere, it's going to influence the surface ocean currents, and that can influence other properties of the ocean, mixing the thermohaline circulation and other things. So these are all working together simultaneously into one coupled climate model. And this is the state-of-the-art models today. It's not just the atmosphere. The models I'm showing you here for weather forecasting are the atmosphere. We have to model the ocean now because it's part of the climate. We have to model the ice because it's part of the climate. And certainly we have to model what people are doing to the climate as well, and ecosystems and land cover and land use. The climate model has all these components, and it looks like this. Where you'll have models for the ocean down here and measure all those properties of the ocean, models of the atmosphere that will model properties of the atmosphere, land cover models, land use models, models that will also measure things that deal with the snow cover and ice cover. And all these things are interacting and happening and communicating back and forth. It sounds complicated, and it is. But it's also brilliant. It's really great. Let me show you a little loop here of a climate model simulation. This is from a US model, and it's the National Center for Atmospheric Research Climate System Model. It's actually a later version of the model, but what they're showing you here is atmospheric water vapor. You can think of it as cloud cover. It's not exactly that, but it's close. And you'll see that it does a pretty good job assimilating the moisture in the tropics. You see here's a tropical cyclone moving in to East Asia right now. There's storms that are spiraling off the tropics and moving into the Southern Ocean, the world's stormiest place. There's systems moving across the US all the time. This is August. Let me play it again. There's no line of code in these models to tell it to create a tropical cyclone. There's no line of code to tell it precisely that there should be a lot of moisture here. It's the physics of the world, the imbalances of energy that are happening that create these patterns that you see in the model. I think it looks quite impressive when you consider all the things that are going on. But here's the sad news. It's wrong. It's wrong. I'm transparent, telling you the truth. It's wrong, but not in the way that you might think. What do I mean by it's wrong? You might think of it as wrong as a forecasting model, that this is going to tell you exactly what happens on August on any given day. No. These couple climate models do not work that way. They're actually working to tell you what an average August might look like. One model is going to be completely different than the other model because they're doing all these processes in a slightly different way with slightly different initial conditions. And there's no guarantee. In fact, there's actually the probability of this actually ever matching up with an August month on Earth that we experience is basically zero. That's why it's wrong. But it's still incredibly useful. Most models are useful. I taught at the talk, all couple climate models are wrong. Some are useful. That's probably a little pessimistic. We're improving quite a bit. Most of them are useful. The ways that we determine if they're useful or not is, does it look like the Earth? I think it does. You have to kind of take a step back and look at the forest for the trees. You can't look at an individual tree and all the factors that influence that tree, like its soil moisture, the amount of sunlight it might receive, the amount of rain it might receive, how big its leaves are, how much does it reach up to the canopy, top of the canopy. All these factors influence that one particular tree. But if you zoom out and look at the whole forest, you'll find many things in common amongst that whole forest. We're looking at the forest, not an individual tree. So the way that we can verify if they're right is if do they mimic the Earth? Do we see patterns that look like the Earth? And are they reproducing things that we've seen in the past? Are they useful and skillful? And do they provide more information than a simpler system? And most models do. One of the things that I think is crucial here is their utility. Even though they are wrong, even though they're not producing the exact Earth as we see it, they have a very powerful use. And that is that we can play with them, and I'll call it, we can kick them. Climate kicks. Things that change the climate, that make it different than it was before. What are some possible climate kicks that you guys can think of? What are some things that might change the climate? People. Brilliant. Volcano eruptions. Let me start grouping these a little bit. Good? Yes. Plants. I'll put this, that's a tough one to group. Let me put it actually here. I'm going to group it into land use, land cover. Deforestation might be something that falls in that category. Yes, Michael. Good. Solar output varies every 11 years. We have a maximum sunspot activity, maximum radiation that comes in 11 years. We're kind of actually in a downswing right now, less radiation from the sun. Okay, good. Let's put this down here. Physical processes. They may change the climate, but they're definitely going to be more of an impact on the weather side. But if there's a change in the frequency of those, or the intensity, that would be something. Yes? Absolutely. Greenhouse gases, huge player here. Yes. I'll call this Earth-Sun geometry. This has a huge player on climate change and climate variation on the order of geological timescales, going back thousands, hundreds of thousands of years. We have changes in the way the Earth is oriented with respect to the sun. Sometimes we're closer to the sun than others when our orbit becomes more eccentric, more like an oval. There are other times when our tilt of the Earth, people call this the wobble, it changes. And also the precession of the equinoxes, the timing of the equinoxes varies on geological timescales about every 20,000 years, or 11,000 years, that cycle also changes. So those are properties related to Earth-Sun geometry. There are others, but just to group these here, most of these are human-caused changes. We've altered the system, changed the land use, the land cover. We've introduced greenhouse gases into the atmosphere, things like methane, carbon dioxide, nitrous oxide, ozone, water vapor, through our activities, mostly through fossil fuel consumption, but also through transportation and those sorts of things. Here, these guys, I'm going to put into a group called natural processes. These are things that happen, that would happen without us even being on this earth. All right, volcanic eruptions, we don't, to my knowledge, and I'm not a geologist or a person that studies that, I don't think we cause volcanic eruptions, and nor can we really prevent them. Solar output, we really can't yet control what happens at the sun. And Earth-Sun geometry, this is well beyond our, I think, our ability to alter right now. So these things are happening naturally on the Earth, but do obviously influence the climate. And then natural physical processes, I'll call these internal processes. Things like hurricanes, but also La Nina and El Nino and other climate modes. Those things happen internally to the Earth. These natural processes are somewhat external to the Earth. And so I'll call these again, the anthropogenic climate changes. Things that have happened because humans have altered the climate in such a way. So, why are models useful if they're wrong? And this August will never actually ever happen on Earth because we can add these kicks to the system. Now, before I get there, I'll show you why we have to do these kicks. Why is it important? How many of you believe the Earth is warming? I'm not asking a complicated question. I'm asking, is the Earth warming? I'm not asking why. Is the Earth warming? Some of you, not all of you, great. Almost all scientists across the board and across many different disciplines agree that the Earth is warming. I could show you slide after slide of data that supports this fact. This is just one from a great data set that's gridded across the planet. And the reds are warming, and basically everywhere is warming. Most of the places are statistically significant. When you average across the whole planet, we have a definite signal. Yes?
I think that part of the problem that I had with your question is you said, is it warming? And I was like, relative to what? The Cretaceous period?
Oh.
No.
I understand, sure. Over the last 100 years.
Oh.
Let's go we can actually go 10,000 years and it's still the same answer. 20,000 years, still the same answer. But then if you go back into other parts of geological history, then you have some different problems there, but yes. So the Earth is warming. We also know that carbon dioxide is changing, okay? Here's data from ice core in Antarctica. I love Antarctica. I've been there several times. Ice core data is one of the best ways to understand climate from the past because as the ice freezes, it traps gas inside it. little bubbles of gas are trapped in that ice as it freezes, and we can actually go back in time and measure directly the concentrations of these greenhouse gases. Carbon dioxide, the curve I'm interested in you learning about, is that green curve there. It fluctuates from roughly about 200 parts per million to at most around 300 parts per million in this geological timescales. This data goes back here 800,000 years. All right? So those are thousands of years in the time axis there in the top. And you can see that we've never really been above 300 parts per million in this ice core data. Carbon dioxide also is well mixed across the planet. So even though this is a data core from Antarctica, you'd get a similar result, and you do get similar results from ice cores in the northern hemisphere in Greenland. All right, it's not really dependent upon where it is. Carbon dioxide lives in the atmosphere quite a long time and gets well mixed through the atmospheric processes. Does anyone know where we are right now in carbon dioxide? What's that? 400. Here's where we are. On that same scale of the green curve, 400 parts per million. This last winter at the Earth Observatory in Mauna Loa, Hawaii, they measured 400 parts per million for the first time. Off the charts for the carbon dioxide. So temperatures are going up globally. Carbon dioxide is increasing. We know that carbon dioxide would probably lead to an increase in temperature because it's a very effective gas at trapping radiation from the Earth, not from the sun. It's transparent mostly to the solar radiation, but it does trap radiation from the Earth very effectively and then sends some of that back down to the Earth's surface. That's actually a good thing that it does that. You're happy, whether you know it or not, that it does that because that keeps this planet green and habitable. If it didn't do that, if that gas was allowing everything to go out to space in the long wavelengths of the radiation, we'd be a much colder planet. So the greenhouse effect, this trapping of radiation from the Earth, is good. But adding carbon dioxide like this to the atmosphere, mostly by human processes, human influence, is not so good. But we can't prove that, can we? We show the temperatures going up. We show carbon dioxide's going up. We know that they might be related, but correlation doesn't prove causality. Just because these things are going up together doesn't mean that the carbon dioxide is causing the temperature to increase. We have no way of knowing that for certain if it weren't for climate models. Climate models are that important. They are the tool, I think, and I would argue, that shows this human footprint on climate change. So we can use these kicks in the models to determine their impact. We can run the model one time without just the natural processes here. We can run them again with the anthropogenic climate changes, particularly greenhouse gas increases, but also things like land use cover and the human influence with transportation and those sorts of things, and add those in, right? And we can see the differences. And they are profound. Here's first one demonstration that the models are pretty reliable at doing this. This is, the black curve is the observed data from the global mean temperature. You can see it going up here over the last 100 years, and specifically over the last 50 years, it's really gone up. You can think of this black curve, the global mean temperature, as one model simulation of the real world. We're living in, and the way I like to think of it as a modeler, in one simulation of reality. This is what's actually happening. It's the one thing that's true, right? But in a modeling way, we can think of it as one simulation. The thin squiggles are every other climate model simulation of that real world. Now, they're going to have different timings and different magnitudes of these physical processes when the hurricanes happen, when El Nino and La Nina events happen, so they're going to be different. But when you average them out, you cancel out the noise here in the physical processes, and you leave with the signal, the things that you're telling the model what's going on. And in particular, this slide shows you that after volcanic eruptions, which are all those names that you see in the vertical there, what happens? Temperature goes down, and the models get that. You see the red curve, which is the average of all those models. After all those volcanic eruptions, boom, for sure, the average model simulation gets colder, right? The magnitude of the cooling depends on the model, but sure, they do get the average cooling. And they reproduce the observed data with the warming here in the last 50 to 60 years pretty well. There are differences in 10 to 15 years, and this part here in the end, this climate hiatus or climate pause gets a lot of attention. I don't want to talk about that tonight, but if you want to learn more about that, I'd be happy to talk with you offline or afterwards. But how can we show that humans are causing this warming? Again, apply these kicks. And that's what we do. The top plot here is those models run with both the natural processes, those natural kicks, and the anthropogenic human-induced kicks. And it reproduces the observed black curve pretty close. Pretty good considering how complex and dynamic the climate system is. On the bottom left here, the natural forcings are only applied in the model. In other words, we only allow these things that are happening without human influence that would occur naturally on this planet to occur in the model. And what happens? The average model simulation is flat. In the last 50 years, the temperatures do not go up. In fact, there might be even a slight cooling trend in the climate models with the natural forcing mechanisms only. On the bottom right is the models run with only these kicks. And particularly greenhouse gas increases are the main mechanism. I can show you term by term, kick by kick, what's going on. We can do that. But it's carbon dioxide is the main player here. And you'll see the models actually are too warm. They're warming up too much compared to the observed data, implying that you both need this natural forcing mechanisms. Sunspot activity right now in particular is leading to some cooling in combination with those anthropogenic influences to get the right depiction of climate. This, to me, from the Intergovernmental Panel on Climate Change, the last report in 2013, is probably the most convincing piece of evidence that humans are altering this climate. We see it clear and separate distinction between when these models are kicked without human influence and when they're kicked with it, and both of them together reproduce the observed data. And this is true if we run it separately over ocean and land plus ocean, it doesn't matter. We see the same thing happening where the observed data are only reproduced in those models that include both the natural and the human anthropogenic induced forces. And it's true if you run over every single continent. We can run it separately over different continents. We can run it for the Arctic sea ice extent. We can run it for the Antarctic sea ice extent. And by and large, those models that include both the natural and the anthropogenic forcings simulate the observed climate the best and reproduce the warming trends that we're seeing across all the continents. A pretty strong piece of evidence here for climate change and in understanding the human influence of climate change. But as I said, I have another goal, and that is to convince you that climate change in the future can only be determined by these climate models. So even if they're wrong, we can kick them. And how we do this in the future, we estimate what greenhouse gases might look like. We can't obviously do these things. We can do this to some extent. This doesn't matter because that's geological timescales. We can't predict the major volcanic eruptions that are going to happen. So that natural process is not included in the future. But we have estimates of how greenhouse gases might change. And so we apply these kicks into the future, and we get a simulation that looks like this. The bottom is probably not going to happen, sorry to say. This is if we were to stop emitting gases about a year ago and not change the carbon input in the atmosphere. And then that model simulations show a little bit of warming and then leveling off. The red hopefully won't happen, but is more likely. This is what we call the business as usual scenario, where we don't do anything. We don't really have many mitigation strategies nationally or even internationally to change the climate, and so we kind of just run the world as we've been doing it. And you'll see by the end of the century here, climate models predict a warming globally averaged on the order of 3 degrees centigrade to close to 6 degrees centigrade. Now that might seem like a lot, but this is a global average temperature. The effects are not uniform. The warming is going to be greater in the northern hemisphere, especially in the Arctic, and over parts of Canada and Central Asia, a little less in the southern hemisphere. So there are going to be places that are going to be much, much warmer than 6 degrees centigrade on the planet in the future. Those changes are enough to alter the planet. They're enough to change ecosystems that we live off of. They're enough to change agriculture industry. They're enough to change water supply, especially fresh water supply and snowmelt. They're enough to change our energy consumption and demand, shifting more from a warming, heating world to a cooling-centered world. They have profound impacts. Climate models show us this. Even though they're wrong, most of them are useful. I presented to you tonight the science behind the story. The data speak for themselves. Your responsibility is to take that science and do something with it. You have the opportunity, because I believe humans are a major part of this problem, we also can be a major part of the solution. And that can happen in individual lifestyle choices as well as through international and local policy. But what I hope you can think about tonight is what can you do to make this outcome less and less likely. The time to act, I believe, is now. Thank you. I'd be happy to answer any questions. Yes?
How do you answer the traditional bugaboo about all modeling, that if you throw enough parameters into a problem, you can fit anything
most definitely.
There's an innumerable number of artificial processes you don't have in your model. You weighed every process with a certain weighing factor. You managed to fit the data. How do you know if it will fit it in 5 years or something like that?
Yeah.
I mean, you have to fit old data. How much old data do you have and how well it you fit?
Yeah, so there's a question here about to what degree are you actually fitting the model to the data, essentially, and because we're not including all the processes in the atmosphere or the ocean or in all these different systems. And so is there some model fitting that may be going on here? And that's a great question. And to be completely transparent, the skill of these models and their performance of them does vary regionally. And precipitation, intensity, and locations, and those sorts of things is generally a less skillful thing because that depends on clouds, which we're still trying to figure out how to do well in forecasting. And so in climate things, when these models are producing clouds at much coarser resolutions, they're not doing as well of a job. So there are some differences on other variables, but with temperature and pressure and upper level jet stream patterns, they do a pretty good job. We can see them respond to various things in the past. So if we look at the ozone hole influence on climate, which is another kick here, the response in the southern hemisphere and the change in the jet stream in the southern hemisphere is almost perfectly matched in the models with what we see in observed data. So there are many parameters that match up quite well. And sure, you can find things that are still wrong. These models are not perfect, and nor will they ever be. But I think they have enough skill, enough utility, and certainly are responsive enough to these kicking mechanisms that they have used for understanding not only current climate change, but also into the future. Yes?
To bounce off of what he said, though, it seems to me that the very thing that makes them useful is that they have been fit to empirical data up to this point, that they keep getting refined in relation to what we observe.
That's not exactly true. Weather forecasting models certainly are fit to data and calibrated to data. Climate models are just adjusting, the main fixes that we make in those are adjusting the equations that we use to represent the processes that are occurring in the model. We're always improving our parameterizations of various things, how we represent clouds, how we represent the monsoon, but it's not so much that we're actually fitting it to an individual one event. So the models are still really quite free in the way that they simulate their features. And they won't fit anything precisely together. Nothing will be timed at the same time. We just are understanding the processes better in such a way that we can improve the code. There's over 1 million lines of code in these things. And we're improving the code to represent these processes, which improves our simulation. Another thing that we're doing is we're also improving the resolution. The grid spacing between one point and another point in the model, or also vertically, is becoming finer and finer, which allows us to actually pick up many more features than we weren't before. And that improves the simulation as well. Yes?
So when you talk about climate being an average of weather to some extent, when you do your modeling, in addition to studying the average, can you also look at the variability? How chaotic are the systems? How unpredictable is the weather? People talk about, storms, that they've never seen before. Is that true? Is that something you can examine?
Good question. There's almost 2 questions there. Yes, thank you. So when we talk about climate model and evaluating their skills, she asked, we often use average conditions, like global average temperature. Can models be useful in terms of variability? One thing that we use models for is to understand the frequency and severity of severe events or extreme events. So we can use them to depict like the intensity of hurricanes, their likelihood that they'll intensify, or that severe weather would intensify. We see more likelihood conditions for tornadoes to develop or intense thunderstorms to develop. Also things like drought and heavy rainfall events. We can use models to depict those. But it's always in a statistical sort of thing. We're looking at events lumped together and then the distribution of those events in a statistical way, like looking at the tails of a distribution, rather than actually one individual event. Climate models, like I've said, are not going to ever be used for one event, nor should one ever event like Hurricane Katrina or Superstorm Sandy or Super Typhoon Haiyan ever be used as evidence for or against climate change. Individual events are not climate, they're weather, and so you have to separate the time and space scales there as well. So. Oh, yes. Oh, which one? Someone here? Yeah. Yeah. So the question is how much computer power is used for these climate models, and how do we see that changing into the future? Right now, these models are insane in the amount of computing resources they have. Even just for the output itself, we're talking in terms of terabytes to petabytes of data, not gigabytes like you're used to working with your computers. This is going into terabytes and petabytes, much larger. Processing speed, rooms like this would be filled with one climate model, where you have multiple computers doing parts of the code, and then communicating to the coupler that communicates that code, and the answer is back to the other models. And they'll fill up rooms bigger than this. Some of the most sophisticated couple models are just warehouses of just servers. In terms of our improvements, we've been increasing resolution in space about an order of magnitude every decade. And that's about where the processes were going. So we'll see these things go down more and more finer scales as we move into that. And hopefully as computer processing keeps up with that, we can continue not to increase the amount of processors, but keep them about the same size. So good question. Yes?
You said that we can do something big to change what people do in climate. What do you think that would be for us as all of us?
I think, yeah, so just be energy consistent. Yes, sorry, thank you. I'll pick that up yet. So the question is, what practical uses or tips can we do today to make a difference in the climate crisis that we're having? I think there are several things. Be energy consistent and conscious. How you're using energy, what are you using it for? Do you need to find cleaner, greener ways to produce or consume energy? Switching to solar has been very popular here in Athens. There are a lot of people that do that. It's an expense up front, but it can save you a lot of money and produce cleaner energy. Also just the 3 R's, reduce, reuse, recycle, are big things that can happen on an individual basis. Reusing materials as much as you can, recycling everything that can be recycled, and reducing your overall consumption and need for things is also a big thing. You can also become active. If you are very passionate about the topic, grassroots organizations that are making efforts to adopt policy at local levels, to lobbying on Capitol Hill and trying to inform policymakers about the science and what the science is convincingly telling us, I think are other actions that you can do. And then I think the biggest thing that you can always do is make sure that you're voting for people into office that you think are going to be climate-minded and promoting a future that you'd like to be part of. Absolutely, it's built, so he asked a question about black carbon. Black carbon is pollution essentially that's been settled onto snow surfaces or ice surfaces. It's a big problem in the Arctic. It changes the albedo, so it makes it really a dark surface and absorbs more radiation, and it can kind of accelerate the melt of snow and ice. That process is accounted for in the cryospheric models, these snow models, and we approximate how that will look in the future using various transport equations and how that pollution will get up into the Arctic. So it is simulated in these models, and we can show actually its impact on the radiation balance on the planet, individual of other things. So it is definitely accounted for. Yes, it does tend to lead to a regional warming where those things are happening. So, yes.
To what extent is bifurcation taken into account in these models?
Can you elaborate on that?
Sure. When you reach a particular point in a system where a small change produces a huge alternate result.
Okay, so the question was, to what extent is bifurcation included in these climate models? I think we think of it more as a tipping point, where you might reach a threshold where the system is not going to rebound to its previous state. So one initial thing kind of creates a downstream momentum where it just really alters the system. Like a sea ice extent in the Arctic is one of those things that might have already reached a tipping point in the sense that sea ice is declining pretty rapidly in the Arctic. In particular, 2007 and 2012 were really low years for sea ice concentrations in the Arctic. And it was such low concentrations that the Arctic summer sea ice might not ever rebuild itself and grow back to be present in the summer, and to the extent it was before. And we might have ice-free Arctic conditions in the next 50 to 100 years. Those processes are simulated to some degree in each of the modeling components. They have these physics that govern the growth and the response to various forcing mechanisms, and they can reach this state where the equations are not capped. They can continue down into like this runaway effect. So it is accounted for. I think there's definitely some improvements that can be made in that arena, though.
I'd like to thank Brian again.
My pleasure. Thank you.